Consider the graph of y equals 2 to the x. Now these are typical points on that graph. And this is the actual graph itself. Now let's compare this with y equals 3 to the x. These are typical points on y equals 3 to the x, and we can see that this increases much more steeply than y equals 2 to the x. And we'll change this graph of y equals 2 to the x into y equals 3 to the x like this. So this is now y equals 3 to the x, which is much more steep. And of course we can change it into y equals 4 to the x, similarly like this. Which is steeper still. Now let's consider the gradients of these graphs. If I were to differentiate y equals 2 to the power x from first principles, I would get dy over dx equals 2 to the x times this irrational number, which means that the gradient graph is also an exponential graph times a number which is in this case less than 1. The red graph is y equals 2 to the x, and the blue graph is its gradient. Now let's see what the graphs of y equals 3 to the x and its derivative are like. If I differentiate y equals 3 to the x, I get dy over dx equals 3 to the x times this irrational number. And the graphs look like this. The red graph is y equals 3 to the x, and the blue graph is its derivative. In fact, the graph of y equals 4 to the x and its derivative look like this. So generally, considering y equals b to the power x, we could assume that the gradient is dy over dx equals b to the power x times some constant c. So this red graph would be, for instance, y equals 6 to the power x, and this would be its gradient graph. Now if I reduce the value of b, this happens. So in all those cases, the red graph was the original function y equals b to the x, and the blue graph was the derivative. Now it seems that there must be a place where they actually coincide, and I'll try to find it like this now. There. Now this is very strange, because we would have a value of b such that if y equals b to the x, then dy by dx also equals b to the x. Now this value of b, a more accurate number, would be this number here. Now this is another irrational number, like pi is an irrational number, and we have a symbol for it, and we call it e. So if y were equal to e to the power x, then the gradient dy over dx also equals e to the x. In other words, the graph and its gradient graph are the same. This is most unusual, because usually when we differentiate something such as y equals x to the 6, dy over dx is something different. In this case, dy over dx equals 6x to the 5, which of course is different from the original function. So this new thing that we've just found is very special. In fact, it's the basis of a lot of very advanced mathematics.